hope you had some rest, because the second week is going to be as intense as the first week, if not more. So the second week is going to be more focused on observational cosmology, as you see. So we have three courses, one by David Alonso on large-scale structures and observables, another by Paco Villascusa Navarro on more machine learning in cosmology. And also, I think he's going to use a lot of, how's it called, the Google Colab. So you need to use a browser for the codes, etc. He's also giving a colloquium. Remember, we have a colloquium for the institute, and he's giving a colloquium where he promised he's going to write a paper in real time. Several papers in real time. And then we have another course on CMB by Emmanuel Sham, if he arrives. But and tomorrow we have the dinner of the school, as you probably received the email. And also, you probably received an email about the posters, that we need to rotate the posters so that new posters can be put up. So if you have your posters, you can take down now and let new people put the posters up, okay? Because I think we need that space. So, so let me just say a few words about our first lecturer, David Alonso. So David took his PhD in theoretical physics from the other Instituto de Física Teórica, the one in Madrid, from Universidad Autónoma de Madrid. Then he was a postdoctoral researcher in theoretical cosmology at the University of Oxford and a tutor of astrophysics at Christ Church. Then he moved to Cardiff University with Ernest Rutherford Fellowship. And he, as a good son of, no, we should, okay. He returned to Oxford as professor, prodigal, but should go to Spain. Yeah. But he returned to Oxford as professor and tutorial fellow at St. Peter's in 2019. He's an expert in observational cosmology, of course. He has written very important pipelines. The pipeline, TX pipe, we're going to hear about this, I'm sure. Namaster to measure the angular power spectrum with mass, etc. And also the Core Cosmological Library, which is a super useful tool, which is public and people can use. Maybe we're going to use in this course, I'm not sure. I'm not sure, I really don't know. It's really fun. So, so thank you very much, David, for coming.
Can you hear me? Yes, okay, great. Thanks a lot, Rogerio, and thanks for the invitation to come here. I think first time I was in Sao Paulo was 2018, and it was December, so it was super hot here. So it's great to see that you also get, this is not, but this is summer weather in the UK, so it's actually not that bad, but at least it's, you know, you need a jacket and stuff. Great. Yeah, so we're going to talk about large-scale structure observables, meaning, so the main aims of this course is basically to have a review of what are the main observables that we think about when we do large-scale structure, what are the physics that underlie them, and then what are the cosmological effects that we can actually access through those, right? So let's start just with a few questions. So what are the main large-scale structure observables? So when I say large-scale structure observables, what are the things that you think of? I need people to shout stuff. Sorry? Galaxy clustering, yes, that's probably the oldest one that we have. Yeah, what else? The power spectrum is an observable that is ubiquitous throughout large-scale structure, yes. But in terms of probes, like large-scale structure, what other things do we have? Cosmic shear, very good. Those are the main ones. Any others? RSD as part of galaxy clustering. Yeah, so the main ones that we're going to talk about at the beginning, at least, are going to be cosmic shear and galaxy clustering, right? And the second question is, what do they have in common? Why do we think of these two things as being probes of the large-scale structure? What's their common theme? What are they both probing? These are all easy questions. Say again? Lensing, I mean, cosmic shear is lensing. Galaxy clustering is not necessarily lensing. Yes, exactly. So both of them are ultimately probes of the one thing that we would actually want to measure if we could, but we can't, which is the matter over density, right? Which we define as rho at some position in space and time minus the mean value of that divided by the mean, right? Matter over density. You've seen this before. This thing then is a field that depends on positions in space and also time. All right. So ultimately, this would be the thing that we really want to measure, right? So if we could, we would actually look at that. There's other probes, for example, clusters. I'm not going to talk about this. I'm going to talk about mostly things that we think of as kind of fields defined in space. But the thing that they have in common is that they probe the matter over densities, right? So ideally, we would like to see this, not this necessarily. There's many others, and we'll talk about those later in the week. So you have CMB lensing, which is lensing, but from the CMB. But many other very interesting ones, like Sunyaev-Zelovich, the cosmic infrared background, X-rays, gamma rays, 21-centimeter maps, etc. Right, so just to get us started, as I said, the main aims of the course is to review the physics behind all of these probes, discussing the information that we can obtain from them, the main caveats and systematics that we need to be aware of when we analyze them, and then in practice, how we actually extract information from these probes, okay? So before I get started, I'm going to clarify a few things, or basically clarify the nomenclature a little bit. Let me see if I have some of that here. All right, well, so first of all, I'm going to assume that you're familiar with homogeneous FRW cosmology and a little bit of perturbation theory, and after last week, I think you should be. And also that you have some familiarity with the lambda CDM model and what the main cosmological parameters are. So if I write H naught or omega m or W, you're not entirely surprised by that. Great, okay. So some additional nomenclature. I'm going to be assuming natural units. So for the most part, you shouldn't be surprised if you see some H bars and Cs that are missing, because I'm using those units. For me, I'll use this symbol to denote the radial comoving distance. As a function of redshift. And H will be the expansion rate as a function of redshift. And so using my natural units, for example, that means that the relation between the two of them is just an integral in redshift, okay? Yep, nothing surprising about this so far, okay? Because we're going to be talking about fields in a second, one of the things we like to do to fields defined in space is to take their Fourier transform. So I'm going to use the following definition for the Fourier transform, which I think is the same one that Roman was using last week. I snooped through some of his lectures. So if we have a field f of x, its Fourier transform, which I'm going to go, often I'll just call it f of k. Sometimes I'll put a sub-index here instead of putting it there, because I'm used to both notations. But if I can, I'll try to be homogeneous and just call it that. F of k, this will be an integral of f of x times e to the minus I kx over the whole volume. Okay? And therefore, if you want to do the inverse Fourier transform, f of x, if you decompose it into plane waves, it's an integral over the Fourier space volume. And here's where the factors of 2 pi enter, okay? And the rest is basically the same, f of k. Okay? Great. I think that's all for notation. So let me see what else I wanted to say before we get started with the math. All right, so just roughly to give you an idea of what we're going to be talking about, this first lecture is mostly going to be about making sure that we're speaking the same language and that we have the same intuition when we talk about large-scale structure. So there will be some overlap with what Roman was talking about last week, but hopefully with a different angle and a couple other things that were not covered. Tomorrow, we'll talk about weak lensing. Wednesday, we'll talk about galaxy clustering. This might take us, well, I'm not sure, because we'll see how long things take us, but it might be that this actually slips into Thursday a little bit as well. On Thursday, we'll talk about other observables like Sunyaev-Zeldovich, CIB, other radio observables. And then on Friday, we'll talk about the more practical aspects of large-scale structure, meaning how do we start with some data and then go all the way to cosmological parameters, okay? All right, so let's start with the large-scale structure crash course. So before we actually start talking about the physics of large-scale structure, let's talk about the maths that we need for that. And we're going to be talking about fields a lot. So we need to cover some of the maths of stochastic fields. And I think this is something that also Roman covered to some extent, but I just want to make sure that we have the same language. So all the cosmological fields we're going to be talking about, matter over density, if we talk about the galaxy over density, the cosmic shear, we think of all of them as being stochastic fields, meaning, so let's say that we have a field f of x, meaning a field that is not deterministic, right? We only, instead of knowing what the values of the field are, what we know is the probability that f will take values at different positions in space. So this is what we call the probability density functional, okay? This is nothing too complicated mathematics-wise, at least as far as physics or physicists are concerned. You think of this as just a multivariate distribution of a set of variables. Those variables happen to be the values of this field at different positions in space, right? So we should think of fields as vectors, basically defined at different discrete positions in space, right? This is f. And then the values of the field at those points is what defines the field itself, right? If you're a mathematician, then it's more complicated because you should take the continuum limit and realize that actually, in principle, you should be resolving this field at all points in space. But for practical purposes, the best way to think about fields, stochastic fields, is just random variables at different points in space, okay? The fundamental question here is it the right picture to think of cosmological fields as random fields? And I think if you believe in inflation, it definitely by construction is the right way to think about that, because inflation gives you a natural stochastic process that generates the initial density fluctuations, right, through quantum fluctuations. But even if you don't believe in inflation, once you have a sufficiently complicated system, right, that is described by these fields, then it will actually look stochastic, right? There's too many variables for you to track it. So the stochastic picture for cosmological fields is useful, I think, regardless of whether you believe in inflation or not. All right, so the main thing we're going to talk about is expectation values for our fields, or correlators. So for example, the two-point correlation function between 2 points in space is the ensemble average of the values of the field at those points in space, right? So what would this be, probabilistically speaking? This would be the integral over all possible values of the field in point 1, all possible values of the field in point 2 of f1, f2, p of f1, f2. I'm obviously using a shorthand here where f1, f2 is the value of the field at x1, at x2, okay? And it's useful to think about correlators because these are things that we can calculate from real data. They summarize a lot of the properties of the fields. And also we can use them to express important properties of these fields, mathematical properties of these fields. And so a very important one, because a lot of the physics is built around the concept of statistical homogeneity and isotropy, is those concepts, right? So statistical homogeneity. So that the only thing this means is that under a redefinition of our coordinates from x to x plus a constant vector for all your coordinates, let's call it a, all correlators should be the same, right? So that means that f of x1 plus a f of x2 plus a should be the same as f of x1, f of x2 for any a. And there's vectors in all these things. Sometimes I'll forget that I'm writing vectors, but yeah. All right, so that's statistical homogeneity. We also have statistical isotropy. And statistical isotropy is a similar symmetry of Euler correlators. This time it's not a symmetry under displacements, it's a symmetry under rotations, right? So the statement is f of r times x, where r is a matrix that represents a rotation, times f of r times y is the same as f of x times f of y, right? In other words, the statistical properties of our fields look the same no matter what direction we look at in space, okay? And this is for all rotation matrices, for any rotation matrix, you know, in the SO3 group, let's say. Okay? I should say, feel free to interrupt me whenever you want. Just raise your hand or even shout at me if I'm not looking at you, okay? So I'm not saying that all stochastic fields need to satisfy this, but cosmological stochastic fields should satisfy this, right? Unless there's observational effects like right space distortions, which you saw last week, which can break that in the observed field itself because of the privileged position that we occupy as observers, right, in our observations. All right. And then finally, another property that is important is something that describes the distribution, the multivariate distribution itself. And the most useful distribution, I would say, for cosmology is that for Gaussian random fields. And as you saw last week, most large-scale structure fields, in fact, probably all large-scale structure fields are actually not Gaussian and are actually pretty far away from Gaussian. But we think that the initial conditions of those fields were quite Gaussian. So it's still useful to try to understand the properties of Gaussian random fields because they also, you know, they can give us intuition as to how to treat other non-Gaussian fields. And this is just, so the Gaussian random fields are just fields whose probability distributions, let's say F1, F2, Fn, are just multivariate Gaussians, right? So if I write the values of the field at n points as a vector, let me call it F, then this is just given by 1 over square root of the determinant of 2 pi times a matrix C times the exponential of -1/2 of F transpose C to the -1st F. Okay, where C is what we call the covariance matrix. Cij is just the 2-point correlation function of our field. And I'm assuming, and I'll continue doing that, that all the large-scale structure fields that we have 0 mean, right? So that's why there's no F minus F mu or something like that in here. So there's a few things that Gaussian random fields satisfy, which are useful to know, and I think you saw some of those, or maybe all of those last week. First one is that odd correlators are 0. Okay, so the 3-point function of a Gaussian field, the 5-point function, etc., they're all 0. The even correlators satisfy Wick's theorem. And this is something that you've seen if you've seen any kind of quantum field theory or anything like that, right? The idea, for example, if you're trying to compute a 4-point function, F1, F2, F3, F4, is that for Gaussian random fields, you can express that as products of 2-point functions for all the different pairings of your field, right? So you can couple this with this, and you would get F1, F2 times F3 F4. Another pairing, you could put 1 with 3, for example, and then you have to put 2 with 4. So you'd have another correlation, which is 1, 3, 2, 4. And the last one would be pairing 1 with 4 and 2 with 3. And that gets you the last one, right? But there's a very interesting consequence, right, that comes from this. Well, it already comes from the fact that all multivariate probability distributions have that particular form. But you can see it also in terms of correlators. All of the information encoded by a Gaussian random field is encoded in its 2-point function, right? Once you know its full 2-point correlation function, you know everything about this Gaussian field, right? Not only that, but we said that if we have a Gaussian random field, which is also statistically homogeneous and statistically isotropic, then this leads to an extreme version of data compression, right? Where we can learn everything about this field from a single function of a single variable, which is what we call the correlation function, psi of r, which would be, I'm going to call, for example, the correlation function of field f, I'm going to call that psi f of r, would be f of x plus r. Right, so the correlation between the value of f at 2 different points separated by a distance r. And because I'm assuming that things are isotropic and homogeneous, I'm not writing a vector here, right? This is a single variable, just the modulus of r. Sometimes we will look at cross correlations between different fields, right? So we could have 2 different random fields, f and g. And to clarify that I'm taking a cross correlation, and that's what a cross correlation means, I'll write both of them as superscripts as well. Okay. All right. And then finally, as I said, one of the first things in cosmology we like to do with fields is taking their Fourier transform. And it's by analyzing the Fourier transform of stochastic fields that we can define the power spectrum. All right, so let's consider the Fourier transform of a field, f of k. If we do a coordinate transformation, right, a shift, for example, like this, one of these transformations that just shifts all coordinates by a constant vector a, then the Fourier transform goes to f of k times e to the minus I k times a. Okay. So now we should think, okay, what's the what happens with the correlators of the Fourier transform, right? So if we think of this correlator f of k prime. Okay, so under one of these shifts, this will go to f of k times f of k prime times e to the minus I k plus k prime times a. But if the field is statistically homogeneous, then this should be the same, right? After the transformation. So that's only true if k is equal to minus k prime. If we want for this to be satisfied for any value of a, right? So then that means that for statistically homogeneous fields, the only components of the 2-point correlator in Fourier space that are non-zero are the ones that have here k and here minus k. Okay. Not only that, but remember from the definition of the Fourier transform that I put over there, for real valued fields we have that f of k, or f of minus k is the same as f complex conjugate of k. Okay, so that means that the only combination that we should worry about when we take 2-point correlators of statistically homogeneous fields is the correlator of f with its complex conjugate, basically at the same wave number. And that's how we define the power spectrum. So the power spectrum is defined as the correlator of f at k and f at k prime. Let me put a complex conjugate here. Being equal, so it must be proportional to the Dirac delta of the two wave vectors, right? K minus k prime. And then the normalization we choose is that this is 2 pi. There's a prefactor of 2 pi to the power of 3 here, and then that defines the remaining factor, which is what we call the power spectrum P of k. And when I'm talking about the power spectrum of f, for example, I'll just write it either down here or up here, depending on whether it's more convenient. Pf of k, right? And again, as before, if I'm taking cross correlations, because we'll do that a lot, of two fields, f and g, then I'll write that like this. Okay? Okay. Let's go back and consider the 2-point correlation function, because there should be a relationship between the 2-point correlation function and the power spectrum, right? So if we take this definition of the 2-point correlation function and then we write f and g in terms of their Fourier transforms as they were defined over there, what we get is that psi fg of r is equal to the integral d3k d3k prime divided by 2 pi to the power of 6 of e to the minus I kx e to the I kx plus r. And then we would have the 2-point correlator in Fourier space of this, but we can substitute that in terms of the power spectrum. So then we'll get a 2 pi to the power of 3, Dirac delta of k minus k prime, and then the power spectrum. All right, so that simplifies things a lot. This is a 3. This cancels one of the integrals, and it cancels the dependence on x, as it should. And then you get a very simple relation between the correlation function and the power spectrum, which is that one is the Fourier transform of the other. Okay. And this is a lot of math, and some of that you've probably covered already, but I wanted to cover this because there's something that's interesting about this relationship, which is what happens at r equals 0. Okay, that's what we call the zero lag correlation, or in other words, if you're thinking about the correlation function of f with itself, at r equals 0, that's just the variance of the field itself, right? It's just the ensemble average of f squared. So often we'll call that just sigma f squared. And so that means I would substitute this with r equals 0. So there's just that. It's just an integral over the power spectrum over volume. If I write this in spherical coordinates and integrate over the angles, which are irrelevant because I have statistical isotropy, then I get this nice relation that says the variance of a field is an integral, a logarithmic integral in the wave numbers of this factor, k cubed pf of k divided by 2 pi squared. And that's important because this is a quantity that we think of a lot in cosmology. That's essentially, well, we often call this big delta f of k. And some people will refer to this thing as the power spectrum instead of p of k. And mostly because it's a dimensionless quantity that tells you the amount of variance of the total field that is accumulated in a logarithmic interval of k. Right? So it's kind of like the amount of variance per logarithm of k per decade to some extent, or something like that, in in the field, right? So it's something that is useful to think about if you're trying to think about, okay, when does my field, for example, become nonlinear? When does it start taking values of order 1? And what scales are the ones that will bring it to those kinds of values, right? It's a nice quantity to look at. Okay, this is all I'm going to say for now about stochastic fields. Any questions? No? One thing, actually, there's one other thing that I'm going to say about stochastic fields before I move on, which I think is actually crucial, especially if we're talking about observables. I'm just going to write it here, which is something called the ergodic theorem. So the ergodic theorem is the main thing that justifies why we're able to do large-scale structure and cosmology in general from stochastic fields, right? Because so far, I've just described this thing, right, the correlator, as some kind of mathematical manipulation that we do of fields, right? But in reality, we don't have access to multiple realizations of our fields so that we can take these averages over those realizations. What we have is a single realization of, let's say, the matter over density field or the galaxy over density field or something like that, right? So if we want to compare theoretical predictions for power spectra, for example, with what we have in a given field, then we need to be able to compute power spectra from those fields. And the ergodic theorem is what tells you that you are able to do that, okay? The ergodic theorem is something that applies to fields that are statistically homogeneous, but also to fields that are uncorrelated on large scales. And what that means is that if you have the ensemble average of the field at positions, let's say, x1 and x1 plus u, at the limit when u goes to infinity, or even let's say that we have more of these, right? So you have x1 plus u, and f of x2 plus u, for example. Then in the limit when u goes to infinity, what you end up with is you're basically the fields that are very widely separated are uncorrelated with one another. So this becomes just the correlator of f at x1 multiplied by the correlator of something like, f at x1 plus u, f at x2 plus u, basically, right? Meaning that you do whatever the value of the field is in this region has, is completely uncorrelated with whatever it is at a very large value at a very long distance, right? Okay, so what the ergodic theorem says, maybe I'll erase here or here, is that you can come up with estimators of correlators from a single realization of the field, and those will be sufficiently accurate, okay? What does that mean exactly? So let's say that we want to calculate the two-point correlation function of a field, right? Let's say psi of, we want to come up with an estimator for psi of r. Okay, and we only have a single realization of the field. How could we calculate it? One thing we could do is we could say, okay, I'm going to integrate over a region of space. Let's say the volume of that region of space is V, okay? And what I can do is I can take my field at that position in space, multiply by the field at the shifted position in space, shifted by the shift that I care about, r, and basically average over all such pairs of fields, right? So what I'm doing here is I'm doing that over this region in space, right? And I'm taking, okay, I'm going to take this, the value of the field here and at a different separation, and then I'm going to multiply them, and then I'm going to do the same thing for this place and this other place, this place and this other place, right? So all pairs of fields within my volume separated by a distance r, and then take the average of that, right? So that means instead of taking an ensemble average like that one, I'm taking spatial averaging of the field. So what the ergodic theorem says is that the ensemble average of this estimator minus the ensemble average of this estimator minus the true value of the correlation function goes to 0, like v to the minus 1/2, basically. So as v becomes larger, the errors in your estimator become a lot smaller, right? So that's what the ergodic theorem essentially says. In fact, it's the variance, sorry, the standard deviation of this estimator goes like v to the minus 1/2, but that's the idea, right? That you have fields that are statistically homogeneous so that you can play this trick of just displacing your field within the volume. And if your field is uncorrelated on large scales, which means that you can think of your field in this region and this region as being kind of different realizations, so spatial averaging is the same as ensemble averaging, then your estimators will converge. They will be accurate. You can estimate power spectra and correlation functions from a single realization of the field. Okay. All right. Questions? Yes. It's correlated on pretty large scales, but not infinitely large scales, right? Yeah. So you just need to go to scales that are much larger than whatever the correlation length, the typical correlation length is of your field. And it's true that the CMB has large-scale correlations at the level of a few degrees, but the sky is 40,000 square degrees, so you can still play this game. Yeah. 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 Yeah, it's a complicated definition. I think there's different people will define it in different ways. I like to think of just taking the correlation function, kind of, right? Psi of r. If we're thinking of delta, for example, psi of r, and I would say the correlation length is whenever the correlation becomes sufficiently large, right? So if it becomes of the order of 1, I would say that's roughly what the correlation length is for the density field, basically. But there's other kind of mathematically well-defined definitions. Depends, if anyone says correlation length, you should probably ask them exactly what they mean by that. What I mean is, the distance beyond which the field values are not actually that correlated with one another. So the level of correlation between them is small. Yeah. Yeah. Yeah, in practice or mathematically? In practice, you need to do lots of tests, right? And obvious tests that you can do is, well, what's the main assumption behind this way of estimating a correlation function? What I'm doing is I'm saying, I'm going to take averages of all the different pairings that I have within my volume. And this is assuming that, that I can take the value of of f in this region as being equivalent to a random realization of the field, just like it would be in this other region, right? So an obvious test that you can do is, if you split your survey into 2 halves, do you get consistent measurements of the power spectrum, for example, right? So you test your assumptions that way. And very often the answer will be no, but not necessarily because the estimator is wrong, but because you have systematics in the data, and then we'll talk about that as well. Yeah. Does that make sense? Yes? And also, I mean, the other thing is, first of all, statistical isotropy and homogeneity to some extent is one of our assumptions that we can test that way. The other one, which is whether the field is uncorrelated on large scales, you can test by trial and error, right? Compute the correlation function. Does it go to 0 at large values of r? Then if so, then you're probably safe in assuming the ergodic theorem. Okay. Great. Let's rush now through a little bit of perturbation theory. Not perturbation theory per se, because you've done a lot of that with Roman, and I don't want to do that again, but maybe some of the main results that you have from perturbation theory. And what I mean by that is I want to review very, very quickly what are the main results in our study of the evolution of the matter over density as a function of time, okay? All right, so if you remember, in Newtonian perturbation theory, the evolution equations for the matter over density are this, delta dot, so this means derivative with respect to cosmic time, plus nabla times 1 plus delta times v. So there's a divergence here is equal to 0. V dot plus 2 times h times v plus v dot nabla times v plus 1 over a squared nabla psi is equal to 0. A is the scale factor, because I think I didn't say that before, but hopefully everyone just calls it the scale factor now. And then finally, the Poisson equation, nabla squared of psi is equal to 4 pi g a squared rho bar times delta. I'm calling the gravitational potential psi. Very often people use phi, but because I will call something called the lensing potential phi, I decided to call it the gravitational potential psi. Okay. All right, so interesting things about these equations. These are non-perturbative, right? These are in principle the full equations you should solve in order to figure out the evolution of delta. I'm assuming that there's no pressure to make things easier. We have non-linearities in these equations, and they come from this term and this term here. But they're quadratic, actually. So it doesn't, the equations are not that nonlinear, right? They're only quadratic, and this is what allows you to have a perturbation theory in the way that no, this one is exact. There's no perturbations going into that one. It's linear by construction, the Poisson equation, yes. In Newtonian perturbation theory is non-perturbative. So in Newtonian physics, let's say, it's non-perturbative in the sense that you could put here a delta of 10,000, right? And the gravitational potential that gives rise to that will be correct, basically. So it's not like in Newtonian theory, yes, yeah. Yeah, all of this is only in Newtonian theory. So yeah, so you have these two terms which allow you to do perturbation theory very easily. You could do perturbation theory in other ways, but the Newtonian perturbation theory at higher orders is not that difficult because of that. But anyway, if we ignore those terms, right? So I'm going to drop that. Then we can take the divergence of this equation, which will involve Laplacian of psi. Then I can use this equation to write everything in terms of v and delta. And then I can use these two equations to write an equation just in terms of delta. All right? And that's the Jeans equation that you've seen in the past. Delta double dot plus, and I'm going to say that this is in Fourier space just to put some spatial labels. Delta dot k minus 4 pi g rho bar delta k equals 0. Okay. All right, so just by looking at this equation and remembering your first, second year physics, what are the main things that you can learn from that? So first of all, this term here, the linear, this is second order ODE, right? The linear term, the one that goes with the field itself, not its derivatives, it has a negative prefactor, right? So think of x double dot minus x equals 0, for example, and this will not be an oscillating result. It will be something that always grows or always decays, right? So that tells you that the density field will either grow or decay. We don't care about the modes that decay in the field, because those will just decay away compared to the growing mode. So, this tells you that you're gonna get a monotonically increasing behavior in the density of delta, in the evolution of delta. Okay. This is not valid. So one thing I said is that I omitted pressure gradients in this equation. So as soon as pressure becomes important, this is not going to be valid. Also, I've dropped all the nonlinear terms. So this is only valid on large scales, large linear scales, basically. Yeah. But this is just to give us an idea of the qualitative behavior of delta, because we'll use it later. So, all right. So this sign here tells us that there will be growth in the density. But we have a term with a positive prefactor that goes with the derivative. And we've seen this in harmonic oscillators as something that damps the harmonic oscillator, right? So this is going to damp the growth, right? meaning that if you had just delta double dot minus delta, you'd get an exponential growth. This is going to make it non-exponential, right? So it will not be an exponential growth. And then there's the fact that all these prefactors do not depend on scale, which means that that growth will be scale independent. Okay. And so the typical growth history that you've probably seen in the past, if we look at the evolution of delta as a function of time. So first of all, what scale independent means is that delta k at a given time, let's say t, is just delta k at t equals 0, or t equal t naught, let's say t naught, which is today, times a function that is only a function of time. That's what we call the growth factor. Okay? So the growth factor is a function that tells us how the overdensity has grown over time, and it's normalized to be 1 today by construction. And that's the normalization that I'm going to use. All right, and in lambda CDM, you know how this goes. So I'm going to use redshift as a proxy for time. Sorry, I'm not going to use redshift. I'm going to use the scale factor because it's going to make my point easier to make. So I'm going to use the scale factor. So we're going from early universe to late universe here. Let's say this is a equals 1 today. And we know that during matter domination, so early times, at least as far as large-scale structure is concerned, that's what we consider early times, D was proportional to A, which is 1 over 1 plus Z. And then at late times, when dark energy starts dominating, then this gets further decelerated, and you get a deceleration basically in the rate at which structure grows. And one of these, right, the departure from kind of growth that is just proportional to a scale factor is interesting. This is caused by dark energy. So one of the ways in which we could study dark energy is by looking at the change in how structure grows as a function of time, right? So one quantity that is quite useful, and you saw that with Roman yesterday, is what we call the growth rate. So it's called the growth factor. This is called the growth rate. Is the logarithmic derivative of this, right? So just essentially the slope of this with respect to A. And you saw, and we will review that on Wednesday, that one of the ways we have of measuring this is by looking at redshift space distortions in galaxy clustering. And we'll see some of that. Okay. So this is a kind of picture that you get if you just do linear perturbation theory. This is something that has been done for a really long time. Last week you saw how to do perturbation theory in general, but at least going to second order in perturbation theory and how you can get predictions, for example, for the bispectrum and things like that from that, or for the one-loop power spectrum. One of the things that you should have realized from last week's lectures, I think, with Roman, is that perturbation theory is a bit of a pain in the ass, right? It involves these integrals over k that you need to solve, and they're a bit annoying. There's the perturbation theory kernels. Just doing things at second order is already slightly annoying to do, right? So it's useful to think whether we can use perturbation theory throughout and just rely on that to do large-scale structure. And one thing we can do is compare, I guess, perturbation theory with exact solutions. And we have one exact solution, which I think Roman might have also mentioned, which is the spherical collapse, right? So there's one configuration for the density field in which we can actually solve this, the nonlinear equations fully without any approximations other than Newtonian versus GR. And even in that case, actually, this solution also holds. Right, which is when the density field is it has spherical symmetry, okay? And in the simplest situation, let's imagine that we have what we call a top hat spherically symmetric over density. So I'm plotting delta in the y-axis here and just position in space x here. And I'm saying I have 0 density, then some density, and then no density again. And it's a sphere of radius r, okay? I think you saw already the solution last week. Should we go over it again? Or I don't know if you actually went through this, the spherical collapse solution last week. Do you remember? No? Something that does something like this? No? Okay, so we can, okay, so at least I can, this will not be for nothing then. Okay, right, so what is the evolution of this, right? So the main, what controls the size of this sphere? It's basically whether it contracts or keeps on expanding or whatever. It's governed by the gravitational forces that would push it inwards, right? And so the size of R is governed by the total mass enclosed within it. So you can just use the second Newton's law and equate the acceleration with the gravitational force. And you know, the fact that the behavior of a given overdensity, the fact that that behavior is completely governed by the mass enclosed within a given radius, that's often mislabeled Birchhoff's theorem. It's not really Birchhoff's theorem. I'm not sure why people call it that. It's not really Birchhoff's theorem. It's just a consequence of the Newton-Poisson equation, right? But anyway, so we can use that equation to follow the evolution of R as a function of time. Right? Let's integrate it over time once, and we can use this trick where we say R double dot is actually the same as 1/2 of dr dot squared divided by R. That's a neat trick. So if you write it that way, then you can integrate over R on both sides. And you get an integral that looks like this, 1/2 R dot squared minus GM over R is equal to an integration constant that I'm wisely going to call E or epsilon. And you know, just by looking at it, you see what's going on here. This is just an energy conservation equation, okay? But this is also, if you think about it, if I rearrange this slightly, this is also the evolution equation for a Friedmann-Robertson-Walker universe in a universe that only has normal matter and curvature, right? So if I divide by R squared, for example, everywhere, this is basically the same as this other equation, A dot squared. So the Friedmann equation is H naught squared omega m divided by A plus omega k divided by A squared. Okay? And what do we know about the Friedmann equation, right? If curvature is positive, right? Is that what I want? No, I want curvature to be negative, right? Yes. So if not curvature to be negative, but omega k to be negative, then how does that universe evolve? What does the scale factor do in a universe with positive curvature? Sorry, yes, with positive curvature, yeah. Sorry? It starts expanding and then contracts, right? And that's kind of what we want this thing to do, right? We want for this overdensity to grow as a function of time, which means for it to contract, right? All right, so that gives us a sign for epsilon, right? So we know that epsilon, if we want a system in which this density will collapse, we want epsilon to be smaller than 0. Okay, so this is the term that looks like curvature over there. Sorry, should be no A squared there. Okay, So in that case, if epsilon is a negative number, this is an equation you can solve by making a change of variables. And you've seen that, I think, when you solve this same equation in cosmology. I'm not sure if you've ever seen the evolution of matter plus curvature universe. But you basically make this change of variables. R is equal to, in this case, gm over 2 absolute value of epsilon times 1 minus cos of theta. So that's the change of variables that you would make. And then t is gm divided by 2 absolute value of epsilon to the power of 3 halves times theta minus sine of theta. Okay. So this is just an implicit solution to that equation that tells you how the radius of that overdensity should change with time. Yep. Yeah. Yes. Yeah. Yeah. Not sure who asked that, but yes. Yeah. That's right. Okay, so what does R do as a function of time? If we plotted, we change theta, and that gives us different values of t and different values of R, and we plotted those together. What you get is a cycloid, so something that looks like that. It's basically the shape. If you had a wheel that turns, let me say a wheel like that is turning, and you paint this end of the wheel, and the wheel is turning like that, this is the trajectory that this point will make, basically. Anyway. So R as a function of t, that's something like that, okay? So at the beginning, this overdensity starts expanding because just the universe is expanding, so it's just expanding with the Hubble expansion. Eventually, it turns around because the gravity within it is larger, right? Has a larger effect. This is what we call the turnaround time. And then eventually, it collapses, right? And throughout this time, eventually, this overdensity will become much larger than 1, and you get nonlinear gravitational collapse. So in particular, if we know R and if we know T, we can also calculate the total overdensity within this sphere. And I'll let you do the math, but the total overdensity ends up looking like this. And this is the actual nonlinear solution that we were trying to find. 9/2 times theta minus sine of theta squared divided by 1 minus cos theta to the power of 3 minus 1. All right, so this is the full nonlinear solution to the equations. We can compare this to the linear solution. We know that the linear solution, let's call it delta L, in a de Sitter space, the linear solution we said, meaning matter-dominated universe, we said that the growth of structure is proportional to A, and in de Sitter, A is just proportional to t to the power of 2/3. And we know how t goes as a function of theta. So the linear overdensity, I'm going to write it here, is going to be proportional to theta minus sine of theta to the power of 2/3, to the power of, yes. Is that right? 1 second. Yeah. Yes, to the power of 2/3. And the prefactor here I can figure out by just matching it to delta for small values of theta, just so that they start evolving at the same rate. And the prefactor is a bit weird. The prefactor is like this: is 3/4 inside, and then 3/5 outside of the power of 2/3. Anyway. That's just a curiosity. This is kind of a weird thing to be doing, because why would we look at the linear overdensity? Well, it turns out that in perturbation theory, it's useful sometimes to track how the true overdensity changes as a function of the linear overdensity. So sometimes we will use the linear overdensity as a proxy for time instead of the scale factor or redshift or time itself. All right, so I mean, based on this behavior, what should we expect the true solution to look like as a function of time? All right, so so obviously when t reaches this point, r goes to 0, so everything is compressed into infinite density, right? So there should be an asymptote here at a time equals to twice the turnaround time. Right, so it should be something like that. And at the beginning, the linear overdensity we know goes like 2 to the 2 over 3, so something like that. I'm going to write the linear overdensity with a different color. And this, and then at the beginning, they both track each other. Okay. So that means that, you know, in the interim, the nonlinear overdensity needs to connect these two regimes, okay? And the linear overdensity will do something else. Okay? There's a couple other times in this evolution that are interesting for us. The first one has to do with the virialization of this sphere, right? So we know that if we had a perfectly spherically symmetric sphere with radially moving particles, then all of those eventually would just collapse into a black hole and you'd get a singularity. But in practice, that's never the case, right? If you have a sphere of dark matter, those dark matter particles will have random velocities. So eventually, instead of just everything collapsing into a black hole, things should virialize, right, into random motion. And so this is kind of this regime here is kind of idealized. That's probably not going to happen, but we can try to figure out at what point a typical sphere would actually virialize. And for that, we can use the virial theorem. We know that when something virializes under a force that is given by the gravitational force, the kinetic energy of your system at that point should be equal to the potential energy divided by 2 with a minus sign. Yeah. Of rho bar. It's basically the mean value of the density throughout the universe. This is something I should have said at the beginning, and I didn't say. This I am solving in an Einstein de Sitter universe, so this is a universe that has exactly the right amount of energy in the background. Sorry, the right amount of density so that it has 0 curvature in the background, basically. So that is rho bar in this case. Does that make sense? Yes, okay. Yeah. Okay, right, so from we can calculate from the velocity, we can calculate the kinetic energy. From R, we can calculate the potential energy, right? And we can calculate the time at which this condition here is satisfied. And it turns out to be satisfied at a point in time that I'm not gonna write. I'm just gonna say T virialization, T vir. But the important thing is that you can then calculate at that point in time what is the value of the overdensity field, and the value of the overdensity field is around 200. Okay, so that gives you an idea of the typical overdensities of things that are virialized. So when we look in a second at an n-body simulation, or when we're looking at clusters of galaxies or something like that, objects that are virialized will have a typical overdensity of in the order of hundreds. Okay, so those are the things. Those are the types of overdensities that dominate most of the large-scale structure, which is a very much non-linear value for the overdensity field, right? It's very far away from 1. Yep. Yes. That's right. Yeah. No. Because it's close enough, and we've already been making this a spherical cow anyway. So yeah, okay, that's the only reason. Yes. Yeah. Yeah. And you know, in cluster science, sometimes they'll use 500 as a value for the overdensity, and that's for completely different reasons. That's the overdensity in regions of a cluster where you can actually see the X-rays of that cluster, for example, because it's very concentrated. So it depends a lot on your applications. But you know, order of magnitude, this is roughly the density at which things virialize. But you're right, yes. And you know, and people have calculated the actual virialization overdensity in not just Einstein de Sitter, which would be the 178 that you said, but in models with dark energy of different sorts and things like that. So yeah. Yes. That's you could think of it in that point of the field, but in this case, what I'm writing is the overdensity within this top hat spherical thing, right? So it's the overdensity of this thing, meaning its total mass divided by its total volume minus the mean. Sorry? Yeah, it would be literally the total mass within the sphere divided by the volume of the sphere, so 4 pi r cubed divided by 3, right? Minus the mean density of this Einstein de Sitter universe divided by the mean density of the Einstein de Sitter universe, basically. EDS, and I'm not sure if I defined that, but EDS, Einstein de Sitter means that omega m is equal to 1, omega k is equal to 0, and everything else is equal to 0, so it's just a purely matter-dominated universe with nothing else. Yeah. I haven't written all the steps of this spherical collapse. You can find it if you Google spherical collapse, and maybe I'm going to try to put this. I'll send you these slides, and you can put them online, and maybe I can put links there where you can find the full derivation. All right, let's look at the actual solution as calculated properly. So this is what the nonlinear overdensity in the y-axis is as a function of the linear. So I'm going to do this weird thing where I say that the linear overdensity is my time variable. Okay. And it's good because this is just proportional to the scale factor in Einstein de Sitter, right? So just think of something that goes like the scale factor in the x-axis. All right, so there's two things that I've already drawn here. First, you have the linear overdensity, which is just the x equals y kind of line in this plot, and then dark blue is the exact solution that we just went through. So that one there. Okay. So one thing that I haven't mentioned that I should have mentioned is that you can calculate the value of the linear overdensity, this one here, at the point where the nonlinear overdensity diverges, right? So at which point it becomes infinity. And this is what you call the critical density or the collapse threshold for a dark matter halo to basically collapse into a virialized structure. And that value is 1.686. It's actually a function, it's something that involves pi and powers, weird powers of pi, okay? But it's just 1.69 or something like that. So the idea is whenever you have a point in space in which the linear overdensity reaches that threshold, you should expect that a halo has probably formed in there. So that's where in this plot the asymptote would lie, okay? And this is the point I was trying to make from the beginning, which is, okay, how useful is perturbation theory? Because we can actually also solve the perturbation theory equations for this same system, okay? And it's actually not that difficult. In under spherical symmetry, the perturbation theory equations become a lot simpler. If you take the perturbation theory equations that you saw with Roman and average over all the angles, because everything's spherically symmetric, you can actually solve it to arbitrary orders very easily. But this tells you at how many orders you would need to go in order to start resolving virialized structures with perturbation theory, right? So you have the solution at second order in perturbation theory here, right? But you want to be able to get to regimes where delta is of the order of hundreds, right, in order to resolve realized structures. Order 10 will not cut it, right? You need to get to perturbation theory orders of hundreds, effectively, right, in order to actually use perturbation theory to resolve those. And this is, so that means that, perturbation theory, as we said, even at order 2 is already slightly annoying. Going to higher orders is significantly more annoying. You would need to go, in principle, to very high orders to make it work to get the fully nonlinear, let's say, matter power spectrum. But even that is not possible, and the reason why is that this is a very idealized scenario with spherical symmetry where perturbation theory actually converges up to arbitrary orders. But when you don't have spherical symmetry, there's no guarantee that even perturbation theory will work beyond the kind of perturbative regime where delta is of the order of 1, right? I have 2 blue lines because one is thick, so this is the exact solution, the one over there, and the other one, the dashed one, is the perturbation theory over it. I just made it very thick so that you could see the order 100 because it tracks it exactly. Yes, yeah. No, it's not the same as Taylor expanding. It's not exactly the same as Taylor expanding, right? It's the, the perturbative, it would be the Taylor expansion of this, but as a function of this, not as a function of theta. Yes, that's right, yes, yeah. It's equivalent to that, I guess. I didn't do it that way in this code, but yes. Yeah. Cool, all right. So this is just to say, eventually we need to rely on things that are not perturbation theory. So let's look at some plots of the matter power spectrum to get an idea of when we can rely on perturbation theory, when we cannot or should not. So this is the matter power spectrum. And you can see 2 versions of the matter power spectrum at different redshifts. You have the linear matter power spectrum, so the predictions coming from perturbation theory, or from linear perturbation theory, and the nonlinear one. And this comes from non-perturbative calculations involving n-body simulations, which I'll show you in a second, at different redshifts, right? So at early times, they both track each other relatively well. I guess at this point, you're all familiar with the shape of the matter power spectrum. We don't need to go over this. I think Roman already said something about this. Yes. Okay. Early times, they track each other up to relatively small scales. So k is of the order of 1 to 10. This is the order, where you're looking at, halo-type objects. But very quickly, even at redshift 3, which is quite early times for large-scale structure, you already have departures from the linear theory quite early on at quite small scales, right? Quite small values of k. And redshift 0, you have significant departures even at the k of about 0.1, which is where the BAOs are, and we usually tend to think of the BAOs as being something, that is a large-scale thing. But even in that case, you need to start worrying about nonlinearities. One thing it's useful to define is what we call the scale of nonlinearity, K and L. And one would think K and L is the scale at which the overdensity of the matter fluctuations is of the order of 1, right? Because at that point, any perturbative expansion is probably going to fail quickly. So how can we define that? Well, we said before that we could calculate the variance of a density field by taking the P of k, multiplying it by k cubed, divided by 2 pi squared, and then integrating logarithmically within a given range of scales, right? And that will tell us the variance of that density field. So we can define the linear overdensity, the nonlinear scale as the scale that we put up here, so the maximum wave number. So this would be log of 0, so minus infinity to the log of this thing, log of k and L. The value that accumulates a total variance of 1, right? So that means the typical fluctuations for the density field in this, up to this scale, will be of the order of 1. So then I need to start worrying about nonlinear effects, right? So this is the definition, or one of the definitions we use for the nonlinear scale. And it works relatively well. So this plot shows the variance of the density field up to a given scale k, right? So on scales larger than that. For the same redshifts as before, right? So you had the stuff at redshift 10, redshift 3, redshift 2, redshift 1. And you have the same calculation of sigma using the linear power spectrum or the nonlinear power spectrum here. And you can see that they start deviating from one another pretty much at the point where sigma itself becomes 1, right? So it's, this definition is a fairly good representation of when you should start worrying about differences in your observables calculated linearly or non-linearly. And the main point I want to make is that as soon as you start looking at redshifts of order 0 to 1, this is actually quite early on, right? This is a really large scales. This is below 10 to the minus 1 inverse megaparsecs, which again, as we said, this is BAO regime. Yeah. Yep, good segue into the next. So this is the power. So the nonlinear power spectra that I've been showing you is not really a calculation, perturbative calculation. This is what we calculate in n-body simulations that solve the perturbation, the non-perturbation theory, the full equations non-perturbatively, right? I'm not sure if Paco, you're going to say anything about perturbations. Sorry, about simulations. Not really. Okay. Paco is an expert on too many things, so he's not going to talk about this, but he's an expert in n-body simulations, right? So the way, how do we, if we want to make predictions in the nonlinear regime, how do we do that? The most robust way of doing that is probably through what we call an n-body simulation, where we put a realization of the density field with initial conditions that look like basically what we think inflation should generate at early times, right? So basically we do things perturbatively up to an early time, and then we let that evolve via Newtonian gravity without approximations from then on, right? So what this means effectively is you generate an initial condition with some, with basically a Gaussian realization, let's say, of the matter power spectrum at early times. Usually, simulations are started at redshifts of several tens, because that's where on most scales that we care about, the density field is still linear. So you do that. And then you need to populate this realization of the density field with particles, right? Which are just going to be tracers of mass. So we populate them with mass particles, and then we let those particles evolve via Newtonian gravity, right? We know exactly what the forces between these particles should be according to Newtonian gravity. That gives us the accelerations of those particles, and then we just let them evolve. And then you get these very nice looking structures. I'm going to see if I can click on the video, and then we can actually see the video.
I wonder.
Nope.
My work is easy because I use ClickUp. Here's how I keep track of all my tasks. I start by brain dumping everything I need to get done.
This is not my laptop, so don't judge me for that. Right, so this is an embodied simulation, basically. So this is a box where you've put particles. The density of these particles resemble what the density of the universe should look like very early on. And then you're letting them evolve as a function of time, marked here by redshift. And what you see is, how you start finding a lot of the matter to be congealed into virialized structures that we call halos. Those halos are connected to one another in a weird way through, let's play that again. What's this? Cyberpunk, okay. All right, well, anyway. Okay, well, just to have something to voice over. Oh, but you can't see anything now. Okay, anyway, let's go back to the slides. It's basically the same picture that we have here, right? So most of the mass ends up in halos or virialized structures with overdensities of hundreds and thousands. And most of the volume is occupied by voids, right, where all of this matter has been accumulated from. So this is what the universe actually looks like at late times. And if we want to do calculations or if we want to have predictions for the nonlinear matter power spectrum or any other large-scale structure observables, usually what one would do is run one of these simulations and measure that quantity in an ergodic way from that simulation afterwards, right? And that's what these predictions come from. So these predictions come from a fitting function that matches the measurements of the matter power spectrum in embodied simulations. It's called HaloFit, that maybe you've heard about. Yes? Right. Well, compatible with linear theory. What I mean by that is from inflation, right? Plus what we know about the hot Big Bang, you know what the linear power spectrum looks like. P of k, right? It looks like, you have the scales that are outside the horizon during radiation domination. You have the equality scale, you have BAOs, and then the damping scale due to radiation. And I think you saw that with Roman last week, right? So we know that this is what the P of k should look like at quote-unquote early times whenever linear perturbations hold. So let's say at redshifts, let's say below, I'm going to say 40, something like that. So on most scales, we saw that linear theory is correct, right? All right, so we have P of k. The other usual assumption that you saw with Gonzalo, actually, is that inflation gives us Gaussian perturbations, right? And so at early times, the metric perturbations are going to be Gaussian, and the matter over density is going to be linearly related to the metric perturbations. I don't know how Gonzalo called the metric perturbations, but let me call it phi. So there's a linear relation between the two of them. If inflation gives you a Gaussian perturbation here, then this is also Gaussian, right? Because they're linearly related to one another. Something that's Gaussian something that is linearly related to a Gaussian variable is also Gaussian. And now what you know is that delta m at, let's say, z of 40 or more should have this matter power spectrum, so you know its variance. And you also know that it has zero mean, so that you have everything you need, right? We said that a Gaussian random field is completely determined by its power spectrum. In practice, what you would do is you would say, okay, the probability distribution for delta k is essentially proportional to e to the minus 1/2 of delta k squared divided by P of k. I'm missing a factor of volume here. There's a prefactor here that involves volume, and I'm just going to screw it up. So I'm just going to say some normalization prefactor. So the variance for the overdensity field is given by the power spectrum effectively with a normalization that I'm not going to try to recall. But you know how to draw numbers from a given probability distribution, right? So what you do effectively is for each k, you generate a random value for the corresponding delta k, and that gives you the initial density fluctuations. And then you need to worry about how you populate those with particles, but that's roughly how you do it. Yeah. Does that make sense? Yeah. And then if you want to worry about primordial non-Gaussianity, then you need to figure out how to generate fields from a non-Gaussian realization that also involves the bispectrum or anything else, but yeah. Okay. I was going to talk about the halo model, but I'm kind of running out of time. So I'm not going to do that. Instead, I'll spend a little bit of time tomorrow maybe talking about the halo model. Or maybe I'll introduce this now and then spend like 5 minutes at the beginning of tomorrow talking about the halo model, and then we'll carry on with weak lensing. All right, so this is what we do if we want accurate predictions for nonlinear observables in large-scale structure. Sometimes we don't want necessarily accurate predictions that involve running a simulation where there's a machine involved and maybe we will not understand exactly what's going on. Sometimes we want also to get some intuition about what's going on. And so one of the tools we have in large-scale structure, which is not super accurate, but it's actually quite useful in understanding physically what's going on in large-scale structure, particularly for describing certain observables, is something called the halo model, which I think is not something you covered last week. No? Something called the halo model. No, OK. All right. So the halo model is basically a kind of an effective theory for large-scale structure that allows you to make predictions, but that are not super accurate, but they give you the right intuition. And so what you can see it basically derives from kind of information that we get from M-body simulations, right? What we said is a lot of the matter in the universe ends up, or most of the matter in the universe, if not all, ends up in virialized structures in the form of halos, right, at late times. So we can't really use perturbation theory to describe the matter distribution at late times because we can't really use it to describe things that have overdensities of 100 or 200, right? But what if we could study the properties of these halos from a simulation, try to understand those, and then use those properties to predict nonlinear observables, right? The halo model attempts to do that, right? So the halo model is a phenomenological approach that allows us to make predictions in nonlinear regime from 3 ingredients. So the first one is what we call the halo mass function. The halo mass function, which we call n of m, basically, is just the number density of halos in a given mass interval. Okay, so how many halos of a given mass you have. And I'm not going to do that now, but we'll see tomorrow that there's a kind of very neat way to actually predict what the shape of the mass function is, right? So this just tells us how many halos of a given mass we have. The other thing we would like to know about these halos, if we want to predict, for example, the nonlinear matter power spectrum, is how these halos are distributed in space. And this is described by something called the halo bias. You saw last week with Roman that if you're thinking about the overdensity of galaxies, naively, a good model to describe how the overdensity of galaxies relates to the underlying matter overdensities is through a linear bias function, BG of times delta, right? You've seen linear bias last week. Yes? Right. OK. So halo bias is exactly the same idea. In order to understand how halos are distributed in space, we need to come up with a biasing relation for them. So how the density, the number density of halos of a given mass relates to the matter over density, right? So we're going to be thinking of the density of halos and how that relates to the matter over density. All right, so we have these 2 ingredients. This tells us how many halos we have and how they distribute themselves in space. This should be enough to calculate the power spectrum, the matter power spectrum on large scales, right? Because now we know how many halos we have of a given mass. That tells us how much mass there is in different, in each of these halos. And we also know how clustered they are. So we know how close together, effectively, they can be, right, in terms of their overdensity. So that should be enough to calculate the large-scale matter power spectrum. But if we want to go to small scales, what we really need to know is how matter is distributed within a given halo, right? How the matter density actually populates halos. And that's what we call the halo profile. So effectively, what we need to know is what the density of matter is as a function of distance from the center of a given halo, and as a function of the mass of that halo. Okay. And so what I'll do tomorrow is just spend, let's say, 5 to 10 minutes describing how we can build a model for these ingredients, and how from those we can make predictions for the matter power spectrum. And the reason why I want to do that is that it will be also useful for us to understand other large-scale structure observables that we'll start looking at afterwards. Okay? That's it. Okay. Thanks.
So thank you, David. So just reminding you that we do have a Q&A session today, so you can ask even more questions. But right now, you can ask questions as well.
Yep.
So any questions for David? Yes. Okay.
Thanks for the lecture. So Roman mentioned about nonlinear perturbation theory, and he mentioned that the second, and the third order you can get some physical meaning, like shape. You can dislocate, and also change the shape of the overdensities.
Right.
And so, but in your plot, we are seeing that we need more terms to correct and get a better profile. But we are not changing, like adding more physics is like more corrections.
I guess you mean, for example, that if you can make even perturbative predictions for the bispectrum, that can tell us something about how the matter fluctuations themselves like distribute in the form of filaments and stuff like that. Is that what you meant in terms of the shape, or?
Yeah, no, it's because he like did a Fourier expansion of the deltas.
Yeah.
And the second and the third ones were related to the shape and changing the position of the.
Ah, right. Okay.
And
Yeah. So in this case, I've not shown any of that, right? Because we have only done this in the simplest possible scenario where you have just a single overdensity that is purely spherically symmetric. So you don't really have any shape information about this, right? The only thing you can say about this overdensity is how large it is as a function of time. And so you can't really get any more information from this particular setup, right? And the main point that I was trying to make there is that even in that very simple setup, if you do perturbation theory, it will take you many, many orders to get to the regime where you can look at virialized structures and things like that. Yeah.
Okay, thank you.
Yeah. It will also be useful for the Halo model. So it's not completely useless that we looked at that, but yeah, anyway. Behind.
Professor, I think you said that something about the matter connecting halos are strange, or they are. Yeah. What do you mean by that?
I think that's when we went into cyberpunk, and then I got distracted. But what I meant to say is that what you see in the late universe is that a lot of the matter becomes concentrated into halos, but also that you can see weird structures, right? If you look at the early universe, everything's just like blobs, like boring blobs. And then at late times, you have this web of structure. You have halos, and then in between halos, you have filaments, which might be made of smaller halos, for example, but you have this kind of cosmic webby structure. And that's what I meant to say by weird. Just that it looks a lot more structured, let's say, than the kind of boring Gaussian initial conditions. And a lot of what we do in large-scale structure is trying to extract information from this, right? So, but this, as Roman was saying, I think last week, this is a marker of very non-Gaussian structure in the density field. So we need to also start thinking about non-Gaussian ways of extracting that information.
Okay, thank you.
Yeah. Any more questions?
Yeah. Hi.
But David, so you were saying that you're going to order 100 in perturbation theory in this spherical collapse toy model, right? But in practice, when you're doing cosmological perturbation theory, the convergence is really tough.
Exactly.
Right?
Yes. Yeah.
So even though you need lots of orders, we are struggling to go to two loop.
Yes.
So can you comment a bit about how useful is this beside the toy model case?
Yeah. Exactly. I think it's not very useful at all, and I think maybe that's the point that I was trying to make with this, right? That even in this toy model where this is, it's not trivial, but it's kind of easy to do this. You need many orders in order to convert to something useful. Right on time. In a realistic case where you don't have spherical symmetry or anything, as you said, perturbation theory is not guaranteed to converge at any order on any arbitrary scale, right? So, and it's very complicated. So I think my point with this is that perturbation theory is useful in some regime, but if we have any large-scale structure observable, and we'll see one tomorrow, that is directly probing the nonlinear scales, you should never rely on perturbation theory, because it's going to be very hard, but also probably impossible, because it will not converge, actually. Yeah.
Any more questions?
Just a really quick one. So in the plot of the power spectrum that you were showing before, which cosmology are you using in this? Because it looks really worrisome to me that the nonlinear things are affecting the BAO scales.
Yeah, this is lambda CDM, vanilla lambda CDM, Planck lambda CDM. This is how redshift 0 works. Yeah.
Right.
Yes.
Yeah. Good to know.
Yes. Well, this is why you have things like BAO reconstruction, right? Because they actually, if you want to resolve more than the first two oscillations, you really need to sharpen them out. Yeah.
Okay. So I don't see more hands. So let's thank David for this.
Thank you.
So we reconvene at 11.